Okay, so let's start. So welcome to the first RISE camp. As you know, RISE Lab is a new lab at Berkeley, just started this year in January, and it will be like all the other Berkeley labs, will be 5 years. And it's sponsored by a large number of companies in industry across many verticals, and is led by faculties in systems, security, machine learning, AI, and architectures. So I'm sorry to have to start with some sad news. So yesterday, Lotfi Zadeh died. He was a Berkeley faculty for, 57 years. And for those of you who do not know him, he was a creator of fuzzy mathematics and has many applications. It is used to control high-speed trains, helicopters, cars, appliances for speech recognitions, especially in Asia. And please join me for a moment of silence for Lotfi Zadeh. Okay, thank you. So how many of you have attended a AM camp or a SPAR summit before? Okay, not as many. So as you know, before RISE Lab, most of us were involved in another lab called MLAB, we developed some of the influential open source projects for data analytics and cluster management, such as Apache Spark, Apache Mesos, and so forth. So MLAB was about doing advanced interactive analytics on batch data, large volumes of data, big data. In contrast, the RISE Lab is about making decisions on live data, real-time decisions. So why is that? Fundamentally, as you see and you are looking today, a lot more and more companies collect data, more and more companies analyze the data. And more of these companies, at the end of the day, what they want to do with this data is to take decisions or actions, which will provide some added business value, which will improve their products. You hear today about how to have do diagnosis in medicine, risk analysis, and trading stocks in financial market, operating a production pipelines, automated cars, and tomorrow automated drones. So the next natural questions, if you believe that indeed the decisions and the actions are as valuable as the data, if you believe that the data is only as valuable as the decision and the action it enables, the next natural question is, what is a good decision? And there are a few things which make the decision good. First, obviously, it needs to be a good decision, to be an intelligent decision. But then you want the decision to be faster, because typically a decision which happens fast is better than a decision which is slow. You want the decision to be on fresh data, because typically when the decision is on a data which is fresh, is better than if it's on the data with yesterday data. And finally, you want the decision to be personalized. So really what we want real-time decisions on live data with strong security. We want to make decisions in the order of milliseconds. We want to make the decisions on the current state of the environment rather than the stale state. And we want to provide privacy, confidentiality, and integrity for the decision. And privacy and confidentiality are particularly important if we want to make personalized decisions. So that's a challenge. How do you make personalized decisions while maintaining the privacy, while ensuring the privacy and confidentiality of the data? So RISE Lab goal is fundamentally to develop open source systems, tools, and algorithms for real-time intelligent decisions on live data with strong security. And actually, the real-time, intelligent, and secure, the first word, the first letter, it makes for the first three letters of RISE, the last letter being, standing for execution. So the focus of this first RISE camp is twofold. Is for you to learn about the first system we have released as part of the RISE Lab research. And you are going to learn about this through a sequence of talks and hands-on tutorials. And second is to provide us feedback. And all these systems are very early in the development, which means that your feedback can have a big impact in shaping the development of these systems. In particular, we are going to focus during this RISE camp on 5 areas. One is reinforcement learning, which is about acting in dynamic environments. Second is prediction serving, how to take a model and serve the prediction based on the model at scale. Third is security, how to provide decentralized authorization authentication for IoT devices and many other devices. Fourth is to provide a data context service to capture the context in which data is created and is used. And fifth is about ease of development, how to bring ML, parallel computation to non-CS researchers. So next, let me say a few words about reinforcement learning and why we are focusing on it. So first, let me say a few things about the challenges we try to address. So think about making decisions. Think about making decisions in real time. And think about making decisions in real world. So you have to deal with an environment which continuously changes. And you interact with this environment. So think about a dialogue system, right? The next answer of the dialogue system is going to depend on the entire sequence of the previous answers of the questions of the humans. For example, for a chatbot. You see more and more health applications now, which makes the decision or give you recommendations on a rich history of how you are, how you exercised, how you ate, and so forth. And of course, things about a game like Go, which basically involves a sequence of moves until eventually the game is won or lost. Furthermore, more and more of these decisions, or the systems which take the decisions, will be mission critical. So this means that they are essential for the function of the system. Think about a surgery robot. Think about an automated drone, self-flying drone. Think about stock market, making decisions to trade, risk analysis, or think about production pipelines. So you make decisions in these environments, and if the decisions are not good, they can put at risk the well-being and even the lives of the humans. It's not only that you have to continuously interact with these environments, but the environments are going to continuously change. And they are going to change in unexpected ways. Think about a self-driving cars, which is going to see some bunch of sheep on the street. Never seen that before. Or maybe another self-driving car, which is seeing a twister. Again, never seen that before. Or even in a game, you may be confronted with a move you haven't seen before. Right? And finally, when you make the decisions, in many cases, you do not know whether the decision was good or bad for a while. Think about a move in a game of Go. You really know whether that was a good move or not when you win or lose a game. Think about a surgery, robotic surgery. You are going to know whether what you've done is good or bad when, at the end, whether the surgery is successful or not. And again, think about a dialogue system, a chatbot. You know that you are successful, that chatbot is successful if at the end provides good explanations or helped the human. So now let me tell you why the existing paradigm in machine learning are not good enough to address these challenges. So let's take supervised learning. Without question, supervised learning has been very successful. You have today real applications which, at some level have changed the world. Speech recognition, image recognition, language translation, and many more. So this is about supervised learning. As all of you know, it's about training a model offline on huge data sets, maybe using sophisticated algorithms like deep learning, and then deploying it, and then presenting a query, like for instance in this case a cat, and the model will label that image with whoever is in that image. So in this case a cat. So why is it not good enough? So say now you present to this model, which is trained to perform image recognitions, a tiger. And the model never seen a tiger. It wasn't in the training set. So what is going to happen? So most likely, he's going to assign a label to this image, and probably still going to be classified a cat, which is not horrible wrong in this case, right? The problem is that, again, if you present the same image, I'm going to get the same answer over and over again. And that will happen until the model is trained again, and in the training set, now you have a tiger. And after that, you are going to get the right answer. Now, a solution to that is online learning. With online learning, you are going to feed the decision result back to the model immediately. And the model is going to be incrementally updated. So in this case, I shown a tiger, it was classified as a cat, it's not good, I'm going to tell the model, actually it's a tiger, the model will learn, and after a while is going to classify an image which contains a tiger correctly. Okay? However, online learning is still not good enough. So why is that? So think now in our application that we play a game. So we want to decide what is the next move. So the query, it's a table with the position of the pieces, and you are going to decide the next move. So now the question, you cannot use real online learning. Why? Because do you know whether this is a good move or not? Actually, it's not very clear, because here you are going, the white, which makes the move, is going to lose. It may lose that bishop, right? So you may have to wait until the end of the game whether to know whether it's a good move or not. So you need to, and this is what one thing reinforcement learning is doing. It's actually to make of this a sequence of decisions. It's going to wait until the end of the game, and now the game was won, so then what it's going to do is going to reinforce all the previous moves or decisions which are made, which resulted in winning the game. Reinforcing means increasing, roughly speaking, increasing the probability to make these actions when you see similar queries. Okay. Now, reinforcement learning uses a little bit different concepts and names. So this input, the query, is a state of the environment. So again, in this case, is a board and position of the pieces on the board. Instead of training a model, reinforcement learning computes a policy. A policy is a mapping between the state and the actions you are going to take when that state is shown to the system. An action, in this case, is moving. It's moving a piece. And then, once you move a piece, you change the state, and you might get a reward. And if you get the reward, you are going to feed back the reward to the algorithms to update the policy. So reinforcement learning is different from online learning, at least in two aspects. First, it can deal with sparse rewards. So not all the moves have a reward, have a label. And these rewards are delayed. They are don't happen immediately. You don't know the result immediately. The second, unlike online learning, which just observes the environment, with reinforcement learning, you can change the state of the environment. You change the environment. So this is just to give you a sense why one of the focuses in the lab is on reinforcement learning. And for each of these topics I mentioned earlier, we developed a system, ray, clipper, wave, ground, and pyran. So next, let me say a few words about each system. This is how they fit together. This is a diagram. It's architecture diagram or stack of these systems. And again, we have a few others, but we are not going to talk about them during this AMP camp. So let me take one by one. So ray, it's an execution engine for highly scalable reinforcement learning and distributed machine learning algorithm. It handles arbitrary and dynamic task graphs, so it's more general than bulk synchronous processing model, which is employed by many successful systems today, including MapReduce and Spark. It handles tasks with very low latency, millisecond level tasks, millisecond level latencies, and has high throughput. It can execute millions of such tasks per second. The second system is Clipper. This Clipper is a prediction serving system. And this it solves the following problem. Once you develop the model, you want to serve these predictions to users, for instance. So what Clipper is doing is abstract away the model trained by a variety of frameworks. So you can train your model in TensorFlow, Spark, MXNet, and even Ray. And you can serve these models without changing the application. It also allows you to combine these models to improve the accuracy of the predictions or decisions. It's horizontally scalable. You just add more resources in order to scale up the system, and also provides you online scoring. Third system is pyran. So think about pyran, parallel computing and machine learning for the masses. It has a serverless architecture, which means that there is no need to manage a cluster. It also provides a Python API. So if you know Python, and if you have an account, say on Amazon, Azure, or Google, you can be up and running and running your large-scale application in virtually minutes. Then we have two foundational systems. The first one is ground. This is a data context services, and it's also a central repository for model. So Ground provides the APIs to capture the context in which the data has been created and it's used. So you can ask questions about who created a particular data, who processed it, who modified it, who deleted it, who accessed it. Currently, there are 2 applications targeted by Ground, Global Data Inventory and Continuous Integration for AI. This is done in conjunction with Clipper. Finally, Wave. Today, more and more data is generated by IoT, smart devices. More and more actions are going to be taken at the edge. And you have a huge diversity of such devices. You have a huge diversity of organization and users owning these devices. So authorization, authentication is a very important problem. So this is a problem addressed by Wave. Connects sensors, actuators, devices, people, and many more. It uses blockchain, so it's totally blockchain technology, in particular blockchain smart contracts, totally decentralized. So there is no unique entity to run the system, to trust. And it provides a strict security model, allows delegation and strong verification. So during these 2 days, you are going to learn about these systems. Today, you are going to learn about Ray and about Clipper. And tomorrow, you are going to learn about Pyran, Ground, and Wave. So next, in the next talk, Alexei is going to tell you a little bit more details what you are going to learn in each of these tutorials. If you have any questions, our wonderful staff, it's out there, Kat, Boban, Carlin, Shane, John, and Jay. And also, we have some wonderful students which are going to help with this camp going well. Finally, I'd like to thank to all the sponsors which make the research possible, which make the lab possible, which make this AmCamp possible. And thanks everyone for being here. I know it's early. I know it's at kind of the end of the weekend, the end of the week. And I hope that you are going to enjoy and find this camp very useful. Thank you.